today at this lunch hour. And today we are honored to have Professor Zhigang Li from Department of Biostatistics, University of Florida. And Professor Li is currently an associate professor with the Department of Biostatistics at UF, and he is one of their preeminent hires. And he is an expert in longitudinal data analysis and structural equation models. And he's the PI of an R1 grant studying mediational models from microbiome research. And he has actually written R packages for the implementation of the methodologies he developed. So it's very productive in microbiome data analysis. And today, Professor Li is going to talk about MedZIM. It's a mediation analysis for zero-inflated mediators with applications to microbiome data. And I would encourage people hold their comprehensive question to the end of the talk. But if you need like a quick clarification of something, then yeah, you can ask during the talk. And thank you so much. And Dr. Li, you have the floor. Thank you.
Okay. Hi, I really appreciate Ming for the nice introduction and also for the invitation. It's a great pleasure to speak on this platform. And I wish I have had the chance to drive down to Tampa to enjoy the beach. I really wish I could have used this excuse to go there, but you know, things are not allowed, the situation is not allowed. So maybe next time I can drive there to enjoy the beach and to meet me. So today I will talk about a research work that we're conducting in my research lab. It is a mediation analysis model for analyzing microbiome data, and it's called MedZIM. So this is a brief outline of my talk. First, I will give a brief introduction of the mediation analysis method, as well as the motivation of our method. Why do we need to develop this method? And I kind of assume that the audience will have some basic knowledge of microbiome or microbiota. That's why I don't have introduction of a microbiome in this talk. But if you have any questions during the talk, quick clarifications, please feel free to stop me to ask me a question. So, and after that, there will be a model construction and estimation, how we construct a model to estimate the associated, related parameters to estimate the mediation effect, followed by a simulation study to evaluate the model performance in comparison with existing other existing methods. So since I'm a statistician, the talk is probably, at least some of the slides will be very maybe statistical to some of you. For example, the model construction, estimation, and the simulation study. But at the end, there will be two real data applications. That will be not, it will be straightforward to understand those applications. So one of the real study application is on human microbiome, and the other one is on mice microbiome. The mice microbiome is actually can be considered as a randomized trial. So what is mediation analysis method? So mediation analysis concerns the intermediate variable that sits in the causal pathway from an independent variable to a dependent variable. And that intermediate variable is called a mediator. So here, as you can see, this is a typical triangle illustration of a mediation analysis. So in here, we have the independent variable, which could be treatment in the clinical trial, could be a certain exposure in observational study, or could be a risk factor in observational study. And then the dependent variable could be disease, right? So there's usually a direct effect from the independent variable on the dependent variable. But then the effect could also go through a third variable, intermediate variable, which is called a mediator. So you can think of this as a very simple two-step chain process. The independent variable will cause change in the mediated variable. And that change, in turn, will cause another change in the dependent variable. So that chain process characterizes this causal effect of independent variable on the dependent variable. And that's called indirect effect, in contrast to this direct effect. And also, the indirect effect is the same as mediation effect. So they're interchangeable. So as you can see that, so the mediation analysis, if you want to estimate the mediation effect, it's a little bit more complicated than a simple regression, because if you do it simple regression, you only estimated the kind of the direct effect, right? This from one variable to another variable. But then this indirect effect involves two effects, two associations. You can think of it that way. So the mediation model will be usually will be more complicated than the regression model. It's usually a combination, a set of regression equations. And with those regression equations, we can give a single estimate of this indirect effect of this mediation analysis that goes through this chain process, and then test that mediation effect. And in our analysis, this mediated variable will be a microbiome, like the human gut microbiome. And this, in the two examples, one of them is the exposure variable, and the other one is the treatment variable. And the outcome is, one is the disease, the other one is the dysplasia score. And later you'll see that in the examples. So in the literature, there have been quite a few developments in mediation analysis. And roughly speaking, they can be divided into two categories. The first one is the traditional mediation analysis that relies on linearity assumption on the effects. This mediation analysis was, I think, originated in the area of psychology and social science, and also was popularized in that area, and then later it's been used in many different areas, including medicine, epidemiology, or other different areas. And now it's still quite popular, and you can see application when people using this traditional mediation analysis in papers. The major disadvantage of this traditional mediation analysis is that it relies on the linearity assumption, largely because its definition of the mediation effect. Because that mediation, for example, the traditional mediation analysis will use the product of limit, product of coefficient to characterize the mediation effect. But you have to have the coefficient to make the product. But the coefficient in some model may be complicated, may not be as straightforward. So the traditional mediation analysis will not be able to even construct the mediation effect. And sometimes this mediation analysis is also, you can see, also called path analysis in the context of structured equation modeling, because structured equation modeling is dealing with all kinds of indirect effects involving latent variables. If there's no latent variables in the structured equation modeling, then that structured equation modeling becomes essentially estimating the indirect effects. So that's called path analysis. It's also a mediation analysis. Now, the second type of mediation analysis method is the potential outcomes framework, or the counterfactual outcomes framework mediation analysis. So this type of analysis is relatively new than the traditional mediation analysis, and it's more flexible because it can allow, it does not rely on the linearity assumption of the effects, and also can allow interaction between, if you see this interaction between the independent variable and the mediator variable in the model. The reason that it is more flexible than the traditional mediation analysis is because it used the counterfactual outcomes to define the causal mediation effect. So that using the definition of the causal mediation effect using counterfactual outcomes is very flexible, is very general, which allows this method does not rely on the linearity assumption. So to understand the counterfactual outcomes, we can look at a simple randomized control trial as an example. Usually two-arm, for example, in a two-arm randomized control trial, we want to compare the treatment arm with the control arm, right? The control arm could be a placebo arm or could be not taking anything, just not taking the treatment. So in that setting, the true causal effect should be the difference between the outcome of the patient taking the treatment and the outcome of the same patient taking the control, right? But a single patient cannot take the treatment and the control at the same time. It cannot take, if the control is not taking the treatment, then the single patient cannot take in control and cannot take the treatment and not taking the treatment at the same time, right? So from a philosophical perspective. So in other words, the definition of the causal effect used the two outcomes. One of them cannot be observed because the patient has to either take the treatment or not take the treatment. So you can only observe one of the outcome, and the other outcome is called a counterfactual outcome, which did not happen. So with the counterfactual outcomes, there is a very good definition of the causal effect. But the bad thing about the counterfactual outcome is that the counterfactual outcome is missing. So think of that from a missing data perspective. So how then, if we use the counterfactual outcome, we need to deal with missing data problem. But fortunately, under some reasonable assumptions, we can use the data, observable data, to get a good estimation of the missing data. At least use the mean of the observed data to estimate the mean of use the mean of the observed data to estimate the mean of the missing data under good reasonable assumptions. In the randomized clinical trial, you can think of the data in the control group is a good estimation of the counterfactual outcomes of the patients in the treatment group had they taken control, right? And then you can use the data in the treatment group as a good estimation of the counterfactual outcome of the patients in the control had they take the treatment. So if that estimation is good enough under those assumptions, then you can use the difference of those two groups, treatment group versus control group, to estimate the true causal treatment effect. So that's why the counterfactual outcomes can be used to define the causal effect, and also under some assumptions we can estimate that true causal effect. And similarly, we can extend that from a randomized control trial setting to a mediation analysis setting. We can define the counterfactual outcomes and then define the mediation effect, and then have some assumptions to be able to estimate the true causal mediation effect. So typically there are 4 assumptions that are needed for a mediation analysis to claim a causal effect, causal mediation analysis from a causal mediation analysis. So all these 4 assumptions are regarding unmeasured confounding. You can think of this as if you think of this from an epidemiologic perspective, you have these 3 causal pathways from independent variable to mediator, mediator to dependent outcome, and independent to dependent outcome, right? So the assumptions is basically saying that there should be no unmeasured confounding in all these causal pathways, A, B, C. So that would be three assumptions. And the last assumption is regarding this causal path from the mediator variable to the dependent variable. So in addition, that there should be no unmeasured confounding. And for those measured confounders on this causal pathway, they cannot be a sequence, they cannot be a consequence of the independent variable. In other words, there should be no causal effect from this independent variable on the measured confounder of this causal path. If that assumption is violated, that means there is a causal effect from the independent variable on this confounder, then this confounder becomes a second mediator in this model, right? Because you have a causal effect from the independent variable to the confounder, and then this confounder has an effect on this dependent variable. Then now you have two mediators in this model, so you should change your model. The model needs to be modified basically to accommodate that. And it's a simple triangle model will not be good enough. So as long as those four assumptions are satisfied, then you can use this triangle model to estimate the mediation effect of this intermediate variable. And that can be considered as a causal mediation effect. Now, these mediation analyses have been well established in the literature. As you can see here, people have started to study mediation effect a few decades ago. But as new data comes out, new challenge arises. And microbiome data is one of the examples. Because of the unique and complex feature of microbiome sequencing data, it's very difficult to directly apply the existing mediation analysis framework to the microbiome data to get a valid result. So some further developments has to be made to appropriately analyze the microbiome as a mediator. And recently there have been some developments, as I listed here. All these papers, well, most of them are concerning the composition of the microbiome data. The microbiome data has several challenging structure. Compositional structure is one of them, and I will touch that in my next slide. And these methods, one important disadvantage of this method is that they ignore the zero-inflated structure, so which is a very important structure of the microbiome data. They impute zero with a positive value. So in a microbiome data set, typically you can see 50% of the data being zero, right? And with that many zero, you cannot just throw them away. You have to deal with them. And in the current literature, very often people impute zero with a small positive number, which could be problematic because you don't know whether the number is true or not. And another associated problem with the zero-inflated data is that those zeros can be truly zero or could be false zero. So this boils down to how the data is collected. When we collect the microbiome data, we want to measure the microbiome data of an ecosystem. We usually take a sample from the ecosystem and sequence the sample to get microbiome data, right? If, for example, if we want to get gut microbiome data, we use the stool sample, and then we sequence the stool and get how many counts of the microbiome data in the stool. So the stool is only a proportion of the gut, likely to be a very small proportion of the gut. So many microbiota that are present in the gut might not be present in the stool, which means you miss them, then it will be showing up as zero in your data set, in your data, especially for those rare taxa. So those zero are a false zero. And those also could be true zero, right? That the person could really missing some taxa. So that would be a true zero. Then there's no way to identify which zero are true zero, which zero are false zero. So that makes the problem very challenging. And a related problem to this microbiome data collection is the compositional structure. Because you're using the sample from the gut to collect the microbiome data, then the absolute count in the sample is not a representation, a representative of the absolute count in the gut. So the absolute count in the sample is only represent the sequencing depth, right? The library size. So when you analyze the absolute count, it does not make any sense. So people will use the percentage in the sample, which is as approximation of the percentage in the gut. So that's called the composition. And the percentage has to be summed into 1. By definition, that's a compositional structure. So which means if one microbe increase, there has to be another microbe decrease because the percentage needs to sum to 1, which is fixed number. So people pay a lot of attention to the compositional structure, but ignore the zero-inflated data structure. And here, because of that, we trying to incorporate the zero-inflated data structure in the mediation analysis. And because the zero value has a very important meaning for microbiome data, right? If you're missing a very important taxa, then you're more likely to get a certain disease, a related disease. So we're developing this method, trying to disentangle the mediation effect that could go through 2 routes. The first route is go through, the change of the taxa on the continuous scale, on the change of the abundance level. The other mediation effect is the mediation go through the binary change, the presence absence of the microtaxa. And these 2 changes could happen at the same time. For example, if abundance of a certain taxa changes from 0 to a positive number, that means it changes on the continuous scale of the abundance level. It also changed on the binary scale, right? It changed from absence to presence. So both of those changes could have some mediation effect. So this is a figure illustration of the mediation analysis. As you can see here, there's 2 mediators now. One is the continuous abundance level of the microbiome. The other one is the binary change, right? And there could be 2 mediation effects going through these 2 different routes happening simultaneously. So how do we, estimate those 2 mediation effects at the same time? Now, here comes some statistical part, the mathematical formulas. So we use YMX, denote the outcome, mediator, and the exposure respectively. And in the mediation model, as mentioned earlier, we usually need multiple regression equations to model all those causal pathways. So this is the equation we needed to model the association between outcome Y and the M mediator and the X. So as you can see here, this indicator variable 1, M bigger than 0, is a binary indicator function. And we also included the interaction between the exposure and the mediator. So if we're using a traditional mediation model, then it will not be able to account for these features. Only the potential outcomes framework mediation can do this. So this model basically models beta 1, beta 2, beta 3, the effects of the associations between Y and all these exposure and the mediators. Also, of course, we included the interaction here. And we still need models to characterize the association between the exposure and the mediator. So before we do that, we need a model for the mediator distribution for the mediators. So since it's a zero-inflated mediator, we need a zero-inflated distribution. So we formed a very general form for the zero-inflated distribution because that's just a mixture of a point mass and another distribution for non-zero values. So it can be written in this way. The script G theta is the probability of the mediator equals 0, and this is the G M theta is the distribution density or the mass function PMF conditional on the mediator is non-zero or positive. So this is a very general formulation. It can be applied to microbiome data. It can be also applied to other different types of zero-inflated distribution. For example, for microbiome data, we usually assume a zero. For the relative abundance, we usually assume beta distribution. Here, we assume a zero-inflated beta distribution. And for that distribution, we have these parameters, mu, phi, and delta. And this is the density function for a beta distribution, with the mu being the mean of the relative abundance, and the phi is the dispersion parameter or the scale parameter. And these are just examples of other different zero-inflated distributions. This is for the zero-inflated log normal distribution. So as long as you specify the parameter and the distribution for the log normal, then it can be used to construct this zero-inflated log normal distribution. And then this is the zero-inflated Poisson distribution. Here, the point mass at zero involves two parameters because Poisson distribution itself can generate zeros. So there's one parameter lambda controls the zero from the Poisson distribution, and another parameter delta star controls the excessive zeros from this zero-inflated distribution. So for all these zero-inflated distribution, we can use this framework to model that. And for microbiome data, we use this. For microbiome relative abundance, we use this zero-inflated beta distribution. So we can construct a very general mediation model. This is the full mediation model. First equation, as you can see, is the association between outcome and the mediator, and the binary mediator, and the exposure, right, the treatment, and also the interactions. And then for the second equation, we model the association between the mediator and the exposure, or the independent variable x. So to do that, we assume a relationship between the parameter theta, because theta is the parameter to characterize the zero-inflated distribution of the mediator M. So by assuming this association between the character theta and the independent variable x, we model the association between the mediator and the independent variable. So this T theta could be in here I wrote it as a single equation, so it could be actually a few multiple equations. Now, for example, if the mediator follows a zero-inflated beta distribution for microbiome data, then we can use this T theta transformation. And then this new one, the new zero, new one. So the equation 2 here becomes these three equations. So the first equation models the association between the mean of the relative abundance and the independent variable. This models the point mass, the probability of being zero between x, between that probability and the independent variable. So then once we have this model constructed, then we need to define the indirect effect. There, in the literature, in the potential outcomes literature, there are two different definitions, slightly different definitions. The one is defined by the Vanderbilt paper, the other one is defined by the EMICE paper, so I call it IKT because those are the initials of those three authors. In IKT paper, they defined the mediation effect for both the treatment group and control group. So they have two mediation effects, but the mediation effect defined for the treatment group is the same as the natural indirect effect defined in Vanderbilt's paper. So I will use just the Vanderbilt's definition. As you can see here, this is the natural indirect effect. So this outcome is a counterfactual outcomes. So by the way, the yx2, mx2 means the outcome of y when x takes value x2 and the mediator takes value at x equals x2. And this is the counterfactual outcome because when x is taking value of x2, m, you cannot observe mx1 because mx1 is the value of m when x takes s1. So by using this counterfactual outcome, we can define this natural indirect effect here. And the expectation means just taking the average. If you just think of that as the average. And also there's definition of the direct effect. It's called a natural direct effect. And of course, the total effect will be equal to the summation of these two. And the total effect, the formula is very easy to understand. It's just changing when the x independent variable changing from x1 to x2. That's the difference of these two outcomes. That becomes the total effect of the x. So we can, under the model we constructed, we can derive a formula for this mediation effect, NIE. And it turns out that NIE can be further decomposed into two components. As we show in the figure, there could be two routes for the mediation effects, right? This is the routes, mediation effect through the routes where the continuous change in the abundance level is the mediator. And then this is the mediation effect through the routes where, you know, the binary change from presence to absence or from absence to presence is the mediator. So we can characterize those two different mediation effects. And as you can see, for the second mediation effect, it depends on beta 2, beta 4. If you still remember the model, beta 2 or beta 4 are the coefficients characterize the association, the effect of the binary mediator related to the binary mediator on the outcome of y, right? So if beta 2, beta 4 equals 0, then this second mediation effect will be 0 because the binary mediator has no effect on the outcome. And also, if the exposure x has no effect on the probability of the mediator being 0, for example, if gamma 1 equals 0, that means the binary mediator is not associated with the exposure variable, independent variable, then there should be no mediation effect through that binary mediator, right? And this will also be 0 because this script g theta x1 will be equal to script g theta x2. So this is the formula for calculating the mediation effects, the two mediation effects. And then the next thing we need to do is to estimate the parameters and then calculate mediation effect and confidence interval. But to estimate the parameters, we need to deal with this issue, the zero-inflated issue. There's a lot of zeros, and some zero are true zero, some zero are false zero. So this phenomenon is similar to missing data, right? For missing data, we don't observe the data. Here, for those false zero, we don't observe the data too. So we assign it to be 0. It's actually missing, right, for the false 0. So we can deal with this similarly as how we deal with missing data. For missing data, usually we assume a missing mechanism, missing at random, complete at random, missing not at random. Once we have that mechanism in place, then we can start to estimate the parameters. So here, the same thing, we assume a kind of mechanism for observing 0. So if we let m star denote the observed value of the relative abundance of the taxon, and m denote the true value of the absolute relative abundance, then this is when the probability that we observe a 0 conditional on the true relative abundance and the library size denoted by L is equal to this. So it depends on the product of m times L, and m times L is actually the library size in here. So if your library size is too small, of course, you'll be observing 0, a lot of zeros, right? If your library size is not enough, you will be less likely to observe 0. So you can think of this also as a from epidemiology perspective, because epidemiology use the LOD, limited detection law. Think of 1 as the detection dimension. If the sample size, if the product m times L is less than 1 for a certain microbial taxon, then you will not observe, you will observe 0, right? So once we have this mechanism, we start to construct a log likelihood function and estimate parameters. So I will just ignore all these details of this. So once we observe the estimate the parameters, we can estimate, the patient matrix, construct a 95% confidence interval. So here is the simulation results. Where we compared our method with several existing methods. The first method compared is the IKT, the E-minus method. And in here, we generated 100 data sets. In each data set, we generated 100 subjects. And when we generated we used the zero-inflated beta distribution to generate the microbial taxon. So we considered two scenarios in this simulation. One is when the taxon has a low relative abundance. And the mean relative abundance is 0.0025. So that means this could be a rare taxon. And it has a lot of zeros in the data, including false zero and true zero. So in this scenario, these are the true parameter values we used to generate the data. For the independent variable x, we generated with the standard normal distribution. So as you can see here, the model performance is really as expected. There's no big bias, and the coverage probability of the 95% confidence interval is around the nominal level, 95%. But if you look at the IKT approach, so at the bottom, there is a huge bias by using IKT, and the coverage probability is only 9%, far away from 95%. So that's because the IKT approach was not developed to analyze the microbiome data where there could be many zeros and many false zeros. So as you can see, if you applied IKT data to microbiome, then you could get very bad results. It's not valid. In another scenario, we considered a relative abundance, high relative abundance. And here, the performance of MedZIM of our approach is as expected. The low, very small bias and coverage probability close to 95%. But for the IKT, it's also not bad because in this case, there's no false zeros because the relative abundance is very high. It's 0.5, 50%. So it's very difficult to observe a false zero, right, for this high relative abundance taxon. So all those zeros are truly zeros. And in this case, the IKT approach can be applied, but it cannot decompose the mediation effect into NIE1 and NIE2, like the mediation effect through the continuous change and the mediation effect through the binary change. And we also compared the approach with the CCMM and the sparse MCMM. Both of these two approaches are dealing with the compositional structure of the microbiome data. So here, when we generate data, different from this setup, we generated all the microbiome using a multivariate distribution. It's called a Dirichlet distribution. It's essentially a multivariate extension of the beta distribution. So we can use this to generate all the taxa simultaneously. And all the mu1, mu2, mu_k plus 1, they are just the mean of the relative abundance of all the taxa. And phi is, again, the dispersion parameter. And all this means has to sum to 1, of course, because of the composition structure. And the library size is generated using the true data from the true data VSL number 3 study data. And I will present this study later. And we consider two scenarios. One scenario is that there's no mediation effect through the continuous change, but there's only mediation effect through the binary change by generating a Y through this model. So when we compare the MedZIM with the other two approaches, I'm sorry, my cell phone is ringing. So in this data generation, we compare the ability of these approaches that can pick up the taxon that's truly having the mediation effect. So when we generate the data, we only assume the one taxon has the mediation effect. So we'll compare, whether this approach can pick up that taxon or not. And we use these measures, the recall precision in F1, and also the bias of the estimated mediation effect, bias percentage, and coverage probability. The recall is basically statistical power, precision, measures how precise the method is related to FDR. So 1 minus precision is FDR. The higher precision, the lower FDR. So this is the comparison result. We only have NIE2 under this setup. Only the binary mediator has the mediation effect. As you can see, the MedZIM has good performance in terms of those measures. The one case that the performance is not that good is when the sample size is 100 and the taxa number is 50. But it's still better than the other approaches, much better actually. And the sparse MCMM cannot provide some of the measures. And the second scenario considered for this comparison is that we assume there is mediation effect through both routes, through the continuous change of the taxa, relative abundance of the taxa, and also the binary change of the taxa. So as you can see, M1 is in the model. And this can be rewritten in another form such that the compositional structure can be taken into account in the model. So under this setup, this is the summation result. Now we have NIE1 and NIE2. NIE1 is the mediation effect through the continuous change. NIE2 is the mediation effect through the binary change. As you can see, the similar pattern as the previous comparison here. The MedZIM has better performance. So the reason is that this CCMM and sparse MCMM, they are not taking the zero-inflated structure into account when they model the microbiome as mediator. I think that both of them need to impute the zero value with another small number so that the method can be implemented. Otherwise, it cannot be implemented. And relatively speaking, the CCMM sometimes can pick some signal. For example, in this case, when the sample size 300, 400, and the taxa is 10, taxa number is 10, the performance of CCM is not that bad. But for other cases, it is the performance becomes not good. So as you can see that the zero-inflated structure could really have a big impact on this existing method, and that's also why we try to develop a new method to overcome this issue. So we also applied the method in 2 real studies. The first real study is the New Hampshire birth cohort study. It is a large epidemiological longitudinal study funded by NIH. This study, it's basically studies the environmental exposures, how the environmental exposures have a effect on the pregnant woman and the children. And the main focus of this study is arsenic, because this study recruit children from New England, but mostly from New Hampshire. Another name for New Hampshire is Granite State. Means there's a lot of granite rocks on the ground, so that somehow comes with arsenic. This study how the arsenic, if people drink in underground water, contains arsenic, how will that have adverse effect on health of pregnant women and the children? And there were roughly, if I remember it correctly, there were about 1,600 pairs of mom and babies in the study. So we applied this method, mediation method, in this study, trying to examine, how the gut microbiome of the baby could have some mediation effect on the potential causal pathway from the, arsenic exposure to the health outcome of the babies. So in this study, the gut microbiome was collected using 16S sequencing, using the stool sample. And after all those data cleaning, processing, we got 195 subjects and 224 genera available in the final data set. So compared to the full data where there are 1,600 people or pairs, this is a very relatively small number because the data collection is still ongoing. And also, the microbiome data started to be collected only a few years ago, but this study, cohort study, started in 2009. So many of those kids already passed the infant period when they started to collect the microbiome data. So this number of subjects is much smaller than the full sample of the New Hampshire birth cohort. And in the data, there are about 85% of the data points are zero, so a lot, zeros. It's very sparse, the data. So we use the relative abundance of the genus, each genus as the mediator variable, and we model that with the zero-inflated beta distribution, and we estimate the mediation effects through the continuous change of the abundance level through the binary change of the taxon, and also the total mediation effect when the exposure variable changes from 0 to 1. So in analysis, the exposure variable is the in utero arsenic level. And the mediator variable is the microbiome collected, adult microbiome collected at 6 weeks of age for the infant. And the outcome, Y, is the total number of infections treated with a prescribed medicine between month 4 and month 12 in the first 12 months of age. And we treat Y is actually a total count here, is a count, but we treat Y just as a continuous variable in the analysis. So what we found that is this genus Fusobacterium that's statistically has a statistically significant mediation effect through the first route, through the continuous change, but we did not find a significant mediation effect through the binary change. And this is the mediation effect estimated with the composition. Well, it's pretty small, although it's significant. So the interpretation would be that, as the arsenic increase, then the arsenic will decrease the abundance, because arsenic is antibiotic, some sort of antibiotic. It will kill bacteria. So with the arsenic level increase, it will decrease this level of the relative abundance of this bacteria, such that it will decrease the total number of infections of the children. So that could be one of the one possible interpretation for this finding. And this taxon Fusobacterium has been well established in the literature to be associated with childhood infection. We also applied other approaches in this data set, the IKT approach and the CCMM. There's no significant findings for those approaches, and the sparse MCSM cannot be applied here because X is a continuous variable. It can only apply when X is a binary variable. So since we estimated all the mediation facts for all the genera, so we constructed a heat map with to show the mediation strength of each of these genera. So in this heat map, each row is a genus, and each column is a sample, a subject, basically. So you can see the signal is very sparse, not many mediation effect here. And then the second study is the VSL number 3. It's a mouse model. So VSL number 3 is a probiotic cocktail to promote 8 strains of lactate acid producing bacteria. This study is basically trying to investigate the intervention effect of VSL number 3 for inflammation associated with colorectal cancer. So this is the study design. First, they use this specific pathogen-free mice, transfer these mice to the germ-free mice, transfer these germ-free mice to SPF conditions and colonize them with SPF commercial bacteria to establish the inflammation. And then after that takes a few weeks. After that, they give the AOM to the mouse to initiate the tumorigenesis. And then the mouse was divided into two groups. One group received this WSL number 3. The other group is a control group, received nothing. In the end, we look at whether the dysplasia score will be different, and the microbiome data was collected at the end too. So there were 24 mice in this study. 10 was treated with the WSL number 3 and 14 served as control. Again, gut microbiome data was collected, and 40% of data has zero, right? So a lot of zeros again. And the OTU, we analyzed OTU in this study instead of the genus with the zero-inflated beta distribution. And we found 2 OTUs. One OTU belongs to the S24-7, the other one belongs to the class Bacilli. These 2 OTUs have significant mediation effect on the dysplasia score. And one of them is a positive mediation effect, the other one is negative mediation effect, and both of them go through the first route, go through the continuous change of the abundance level instead of the binary change. Here we also applied other approaches, but we did not find anything with IKT and the CCMM. The sparse MCMM did find 18 OTUs, but the results were strange because they found those OTUs with the confidence interval not covering 0, but then the width of the confidence interval was 0. So they were 0. Basically, the confidence interval is just 1 point. So I'm not sure if that's a valid result because I asked the authors of that package, they cannot explain that. We also constructed a heat map to show, the mediation strength of all OTUs in this study. So summary, small summary, it's a novel approach. This is a novel approach to disentangle the mediation effect for zero-inflated mediators. We can estimate the parameters through 2 different routes simultaneously. And compared to the existing method, the primary advantage of this method is that it can incorporate zero-inflated structure into the analysis. Some future directions here that we were considering for future projects. And here is acknowledgement of my grant and collaborators. So that's all my talk. Thank you.
Thank you very much, Dr. Li. And okay, we have a couple minutes for questions. Any questions from the audience? Any questions?
Yes, this is Christian here. I have one question. Is this able to deal with random effects? Say I have subjects from different sites, and I'm worried about extra correlation. And a second question is if I'm worried about over dispersion on the abundance level, can it do other types of models like zero-inflated negative binomial, or something like that?
That's a good question. So for the random effects, I think it's complicated. Right now, this model is will not be able to incorporate random effects because we're only considering one time point as the mediator. We're not considering longitudinal data or cluster data at this time point. But I think you can try this model to give you an initial idea, if you have the data ready, to give you an initial idea which one might be, having mediation effects. Now, to answer your second question, for the negative binomial model, it can be the zero-inflated negative binomial can be incorporated in this approach because the construction, as you can see here, the construction of the distribution for the mediator is fairly general, and for negative binomial is a completely parametric model, so we can easily incorporate that into this model, and then based on that model, we can have estimates for the mediation effects.
Great, thank you. That was.
Thank you. And anyone have other questions? Yeah, I have a question, Dr. Li. So your model is like cross-sectional, right? It's like, do you need like a temporal order for between the exposure, the mediator, and the outcome?
Oh, the model does not need that. The model, you can apply this model to cross-sectional data. However, if you want to make a causal relationship with the cross-sectional data, you need to be careful because you don't know which one happens earlier. The causal relationship could be reversed when we only have cross-sectional data.
I see. Yeah, and your method it's applicable to like epidemiological studies, right? It's just the limit to randomized control trial.
Yes, it can be applied to epidemiological study or randomized control trial. So in these two examples, one is observational study, epidemiological study. The other one is actually a randomized trial, the mouse study.
Okay, and I think in your future work, you kind of touched upon it. When you tested the genus, you did them one by one, right? You didn't.
Yeah. That's yeah.
So it would be interesting if you develop a method which has a dimension reduction mechanism to test all the genera together and then pinpoint the field that actually had a mediation effects, right?
Yeah.
Okay. All right.
Quick question.
Yeah, go ahead.
So did you try to look at the computational complexity of this approach compared to other approaches?
The computational, yeah, we did compare that. So one of the approaches, like for the sparse MCMM, this one takes relatively longer time than the others. And the CCMM, when the sample size, I think when the number of text size less than 200, sample size is less than maybe 300, that will be fine. But if it is bigger than that, it will take a long time. I think that's an issue. That's definitely an issue when you have many taxa. If you analyze at OTU level, where you usually have thousands, of OTUs. But for this MedZIM, the computational burden is less than both of these two approaches. The reason for that is because we are not putting all the variables in a single model. So as we mentioned here, if you put all the variables in a single model, that will substantially increase computation burden. If you analyze them one by one, then it can be parallelized and it can be very quick.
Thank you very much.
Thank you. Any more questions? Okay. Hearing none, let's thank Dr. Li again for his talk today. And also I thank you, all of you, to be present today, and hope to see you in the future. Thank you very much.
Thank you, Mi.
Okay, thank you, Dr. Li. That's the end of today's talk. Thanks, everyone. Bye.
Bye.